So here we are, order and big O notation. You could say O, but notice that it's an uppercase O, so they say big O. If the O is lowercase, they call it little o notation. So there's two of those symbols that you can keep in mind of. We probably won't see this beyond this section, though, or very little of it. This limit of, as x goes to infinity, of f of x over g of x, if that is equal to 0, then f is little o of g, which means that g will grow larger quicker than f would. You can actually use this limit of this ratio as a test on if a function is big O of another. This is pretty reliable, just a simple ratio of limits. Not too different from what you've seen in Chapter 2. There's the opposite of little o, and that's this big O notation. Whereas if you have f of x divided by g of x, and x is a fairly large number, but we're not going to go as far as to say infinite just yet. But if this ratio is a constant number, m, could be 5, it could be 20 billion, but as x becomes large, and you still maintain having a constant number, that's you could state that f is big O of g. It's sort of the opposite of a little o notation. So basically, what to summarize it with is that if f of x grows much faster than g of x, the ratio would be a real number for a large value of x. And this big O notation is used a lot in computer science. If you're in the computer science and computer engineering realms, this is a very important topic. And so one example that the book gives is you're searching through an alphabetic record. You have a sequential search versus a binary search. There are two different ways you can find somebody's name in an alphabetized database. And sequential search is basically seeking through the database one person at a time, starting at A to B to C to D, making a comparison of each record. And let's say you have a worst case scenario of a guy whose name is Zachary Zebulon. You'd have to search practically the entire database to pull this record. And that would take a long time, especially if this database is very, very large, like containing 10,000 records. And so when we think of big O notation, we look at the worst case scenario of people like Zachary Zebulon. So this would you'd have to go through all X records. So, and then plus a certain amount of constant time for that takes into where you take into account for the time it actually takes to compare the letters. That's C, and that amount of time is going to be pretty much constant for every record. So it's basically the computational complexity is C times X, but we don't really care ourselves with the constant where C can be maybe like 20 milliseconds per record you're comparing. But instead we just sort of take that out and just say that big O of the f of x is equal to x, where f of x is a function that estimates the amount of time it takes to search through x records. And so if you have 1,000 records, you can have a worst case scenario of 1,000 searches. I mean, 1,000 comparisons. And that would not be an effective search. But there are better methods, like binary searching. Like, for example, we have 4,000 records. The expected value of any record, statistically speaking, if you're going to have a random selection of names you're searching for, it's going to be around 2,000. It's the midpoint between 0 and 4,000. So binary searching is involved with taking the midpoint and doing a comparison. Is this name greater than or less than the name at number 2,000? If it's larger, you've just narrowed your search space by 1/2, and you take your new midpoint of 3,000. If your following search is still shows that it's a larger value, you will narrow your search down to 3,000 to 4,000, and you would guess the midpoint of 3,500. And so you're constantly halving your space taken down to 1/2 of what it was before. The 4,000 becomes 2,000, becomes 1,000, 500, 250, the 125, the 60, 64, 32, 16, 8, 4, 2, and then finally there you found it. And if you're counting through these, you'll find the worst case scenario would be to find a guy like Zachary Zebulon would be 12 tries. In fact, for the most part, most people will be found in about 12 tries. You might get lucky for the most part and maybe get somebody right away, or maybe after 10 tries or longer, but on average it would be no worse than 12 tries. I guess on average, that average would actually be really tricky to figure out. I'm not going to do that. But the binary search halves the solution space every iteration. Anytime you have the space on each pass through, it's actually log base 2. And so the big O of this search method is log base 2 of x. Whereas x is 4,000, log base 2 is going to be very close to 12. And 12 is much better than 4,000. It's a lot faster. In fact, binary searching is a search method of choice for databases. Most databases use binary search or some very closely related type of search to this. Updating spreadsheet tables. Let's say you have a two-dimensional spreadsheet that performs a calculation, and you know how it is when you enter data into a spreadsheet. If you have equations in your spreadsheets, they recalculate automatically when an input field changes. It's a nice feature that they can recalculate it. And many spreadsheets have a feature to where you can disable the automatic recalculation, because sometimes an automatic recalculation can take a very long time to do. And it would be nice to disable that during a recalculation. And so the reason that exists is for exactly that situation. And we'll be considering this. You have this table. It's 30 columns wide and 200 rows deep. And it recalculates. And like I say, you try to grow this table out wider to some very large number A columns and some very large number B rows. What kind of growth of complexity do you get as you make a very, very large table that recalculates? And well, so this is the model we actually use. We look at the worst case scenario. And as these two values become very, very large, we assume that the differences between these two to be small enough to be considered similar. Because after all, let's say you grow these up to the thousands. If so, if so, the chances of this being a square matrix are likely. We assume that that this would be the size of the table would be square shaped, and that would be x times x, which is x squared number of cells to be recalculated. To go through there and recalculate those in this square arrangement would take x square amount of time. So the function that determines the calculation time of recalculating this table is x squared, which means that if you grow your table to very large values, you could potentially rapidly cause your computer to run out of computation time. You will rapidly develop a spreadsheet that takes an extraordinary long time to recalculate. If you expand your spreadsheet to even just a few hundred columns, you will notice your computer becoming much slower. Here's another famous example, and that's swapping numbers. What is the computational complexity of sorting a line of numbers by swapping two adjacent numbers, depending on if they're greater than or less than? So for example, you have a number like 8, you have 6, you have 9, you have 15, you have 3, you have 7. You can compare the first two, and you see 6 and 8. And you think, oh yes, I'll swap those, 6 and 8. Then you compare 8 and 9. They're in the correct order. Then you compare 9 and 15. They are in the correct order. Compare 15 and 3. You exchange those. 3 and 15. You compare 15 and 7, and you exchange those. And so let's go back and fill these existing numbers down. You now have 6, 8, 9, 3, 7, and 14. So one pass through will always put the largest number at the end. And you restart. You count through 6 and 8, 8 and 9, 9 and 3. You will have to swap the 3 and 9. You will have to swap the 9 and 7. So that becomes 7, it becomes 9, and 14 is in the correct place. 3, 8, 6. And so in fact 14 will always be in the correct place. You don't even need to check that again. And now you repeat the process. 6, 8, 8, 3. 3 becomes swapped, and it becomes 6, 3, 8. Then 7 and 8 become swapped, and you repeat, and until 3 is on the left-hand side, and every number beyond that is sorted upwards. So we went through all the numbers one time, so the complexity is going to be at least of big O of x. But we went through it a number of times afterwards to an additional x number of times, potentially, to bring our values into a sorted order. And so this actually lies between big O of x and big O of x squared. But it is closer to x squared, and so we consider that in the worst case. The worst case scenario would be an array where the numbers are sorted in the backwards direction of what you need to sort them to where you'll need to do a swap maneuver every single time you do a comparison. That is what would take the most amount of time, assuming that the swap takes a certain amount of time that's worth measuring. Then you'll be doing the most work by swapping a backwards ordered array. And that would approach big O of x squared. That would be the answer to the computational complexity of example C. There are other sorting routines that that find midpoints and estimate, not midpoints, but estimate middle values of a scrambled array, and will sort them in smaller places. One of but you in smaller spaces. And those sorting algorithms are still larger than complexity of x because each number would still have to be read in. The best sorting algorithm is actually called quicksort, and it was authored by Donald Knuth in the 1960s. That is actually x natural log of x in time complexity. A fairly complicated algorithm to demonstrate, but it is fairly fast. If you're in computer science or computer engineering, you will be familiar with this method. So that concludes really what we have to say about computational complexity. Any questions? Please do put those into the comments below. And have fun. The homeworks will be up soon.